Welcome to RI Data Science. Today, I would like to talk about support vector machines. If you remember last time, we talked about Bayesian classifiers or naive Bayes, and we have also done a tutorial in R, and we have classified data using Bayes classifiers. But Bayes classifier is the Bayesian classifier or naive Bayes is actually a very basic start. I mean, you can also start with other classifiers like logistic regression or something, but there are also more sophisticated algorithms like support vector machines. So today, my focus will be support vector machines. These algorithms, they are pretty useful, especially for because they are useful for both classification and regression problems. So you can use it to predict a continuous outcome data, for example, weight, height, or cerebral count, or whatever, numeric data, or you can also use to classify classification or classification task, or you want to predict the class level of the disease, whether the disease is present or absent, or in our text classification task, we want to classify text data depending on the content of the abstract, and if the abstract is for COVID or SARS classification. That's what we want to do at the end of this support vector machine tutorial. But what are support vector machines? These algorithms actually are one of recently introduced algorithms, actually, which comes in about 29, 30 years ago, actually, which was introduced in 1992 by Vladimir Vapnik, and two of his colleagues. So these guys, they were training an algorithm based on an optimal margin classifier. So this paper was published in 1992. Afterwards, this was the first start, and several other improvisation or optimization have appeared for support vector machines. But what are support vector machines? As I said, support vector machines, you can use them for both regression and classification tasks. That means you can use them to predict continuous data, and you can also use them classification, or for example, if you are in statistics, you can use linear regression for continuous data, and you can use logistic regression for binary data. But in this case, support vector machine, you can use them for both classification and dichotomous or multichotomous data. And the goal of, when you use support vector machines, your goal is to find an optimal separating hyperplane, or that's called decision boundary. So you have to find an optimal separating hyperplane. So let's say in this case, you have two data points, two distinctly classified data points, actually, in this case. So you have the red class labels and you have the green class labels, and your goal is to find this margin, a margin that classifies these two data points. So this you try as many lines as you want while you are tuning this algorithm. So you try to find this optimal hyperplane. It's called optimal because there are the decision boundaries. This is the boundary or the margin. So you have one boundary here and another between the boundary, the red ones, actually, between the red ones and these ones. So this line should be the margin. This is called the margin. The distance between this line and this line is called the margin. So this line will be it should be as maximum as possible. And again, you can also find another one for the green dots, and the points which are really close to the margin, to the marginal line. These are called support vectors, and these are features that consider all the other vectors, all the other points to be classified under this category. And yeah, your goal is to find an optimal. So this optimal separating hyperplane is determined by the maximum distance margin. So a hyperplane is an n-dimensional space that distinctly classifies the data points. So you have, let's say, if you have two data points, two-dimensional feature space, then you may have something like this. So you have x1 and x2, and you have the red points on this side, and you have the blue points on the other side, and then in between you have to try as many hyperplanes as you can, and then finally you try to calculate how much they are far from the hyperplane, and then the margin or the hyperplane that creates a longer distance or a wide margin, maximum length, that would be considered as an optimal margin or a decision boundary. So let's say, I mean, you can consider this as like cutting this cake into two pieces. You have to cut it. Let's say on this part of the cake, you may have like chocolate or something. On the other side, you may have strawberries or something. So if you want to, where do you want to? How do you cut this cake? So you have to try a different knife. Maybe you try one knife, which can cut it properly or something, and you may apply it somewhere on this side and the other one on that. You try multiple ways of, but you want to classify the points. This cakes into two classes. Classes in a sense, you don't want to mix up, like the strawberries should not be on the chocolate side, and the chocolates should not be on the strawberries side. So you have to find an optimum kind of knife, and that's actually the hyperplane. So that is called optimal hyperplane, and that's between this line, the margin, these are the margin, and between this line and this line is another margin. So you have to be, this line has to be as maximum as possible. So then this line to be an optimal hyperplane. And the points, and then the points, these vectors that fall into this line, or fall into the nearest point, these are called support vectors. So in this case, for the red class, we have two support vectors out of how many features, how many points? We have 5 points, and two of them are supporting vectors. And for this one, we have another one support vector. So in total, we have 10 data points, but we have 3 support vectors. And this number of support vectors should be smaller than the total number of points. It should not be 10. That means every point is working as a support vector. So if your classification algorithm is working well, then the number of your support vectors should be as small as possible. Not very small, but smaller than the total number. Always it should be, that cannot be more than that. It should be more less than, but support vector measures is one of the evaluation criteria, is actually how large are these support vectors. So the larger these support vectors are, so there is a high chance of your model is overfitting. You can find really a nitty-gritty detail of this algorithm. It's actually a very complicated algorithm. You can find lots of video tutorials, or lots of materials, which can do a better job. So my goal is actually to do the tutorial mainly in applying it, not in explaining how it works and the mathematical nitty-gritty details behind this algorithm. But if you want, you have lots of other videos. This is one video. So this is for linearly separable text data points. So you have this three-dimensional data. So you apply this separate hyperplane. So this hyperplane is the first thing you have to do is you have to project the data points into a high-dimensional vector space. So you put them in high-dimensional vector space, and then within that high dimension, you apply this hyperplane, which distinctly classifies the red, or the two class labels, the red ones or the blue ones. But in reality, this is not always the case. So in this case, we have a kind of linearly separable data. So it's a linearly separable data point. But in other cases, you have to do lots of other options, and that's solved by kernel tricks, actually by applying kernel functions. So you can kind of fold this hyperplane, and let's say you can put it like a mountain. If you apply Gaussian function or radial basis function, or you can put it in a way. So if you put it in a mountain or in a Gaussian, some of the red points maybe appear on top of the mountain, and the blue ones will appear at the bottom of the mountain. We will see it in more in the next slides. So this is again part of the linearly separable data. So in this case, these guys, they are applying multiple, they are tuning the algorithm. Sorry for the interruption. So these guys, they are applying multiple different kernel multiple different hyperplanes until they find the optimal margin. You see they are applying many different hyperplanes until the margin becomes as maximum as possible. So then the point where the hyperplane finds, the point where this margin gets maximum, and that's where we find optimal hyperplane. So this would be this would be our hyperplane. But if you continue searching and searching and searching, you still could find a better optimal hyperplane depending on your computational cost. You can still continue searching for an optimal hyperplane. So you can find the distance between the margin, between this margin would be, the margin between the two classes would be as maximum as possible. So, you see it's trying many different, many different hyperplanes, many different classified hyperplanes, and finally it finds the optimal one, which actually distinctly classifies the two classes. So in the end, you see, this is our optimal hyperplane, and these are the points, for example, in the red one. So this point here, over here, and then this one here, and these two here, they will be considered as support vectors. And for the green ones, this will be the ones down here, maybe three of them, one here and this one and the other one. These three of them will be support vectors for the green class. But depending on the number of your data points, the number of support vectors, depending on the number of your data points or the number of features, and depending on the number of observations you have in your dataset. This is actually one of the criteria that you can use to evaluate your support vector machine model, because if your number of support vectors is close to let's say the number of observations, then your support vector machine algorithm may be overfitting or something, but you need to closely evaluate. I have tried to read many papers that implemented support vectors, and one of the limitations, they don't report the number of support vectors, but it's really important to report the number of support vectors in your optimum support vector machine model. So as I said, this one is for data that's linearly separable, for linearly separable data, which in reality, which is not always the case, because the world is not in linear, is not linear, so your data may not be linearly separable. Let's say if you have a text data that may not be linearly separable. In fact, text data is, at least in the literature, it has been shown many times, text data is linearly separable. But there are some the data types, or some classification tasks or regression tasks that are not linear. So you have to try multiple other ways of developing or training your support vector machine algorithm. And this is actually what makes support vector machines very flexible, and you can apply them depending on if your linear assumption is not satisfied, then you can apply other algorithms, other kernel tricks, and this problem is solved by applying different kernel tricks. For example, this is one of the data that's not linearly separable. So you see, if you apply a linear classifier or a linear kernel here, it doesn't work. Whichever direction you put your linear classifier, it will not accurately fit its data points. But what you can do is you can fold your these data points, and then you can put your kernel. Let's say the green ones will be, if you apply like Gaussian kernel, you remember this Gaussian graph. So if you apply this radial basis function or Gaussian kernel trick, then the green points will appear on top of the mountain, and then the red ones, these orange red ones, will appear down the mountain, and then at the middle there will be your optimal hyperplane. And the same is true for this. So the ones on the red, they will appear on top of the mountain, and this one will be down the mountain, and this and the middle of the mountain will be your optimal hyperplane, which actually cuts the data points into two sections. The next one would be, there are other kernel strategies that you can apply This is one of the also the popular kernel functions, which is logistic regression. It's just like logistic regression. It's a tangent function, but it's called sigmoid kernel. So you apply sigmoid kernel if you try sigmoid kernel if your data fits very better with sigmoid kernel. And this again another example of radial basis function. So you have these data points. Let's say you have this kind of data points, the red ones. I think when you put them in a two-dimensional feature space, they appear, the red ones are somewhere in the middle, and the green ones are around the green, so around the red ones. So what you can do is you can fold this, you can put it in a high dimensional feature space, and then you can do this kind of dimension. So then the red ones, they will appear like in this kind of structure. There will be this in the top of this Gaussian graph, so they will be on top, and then the green ones, they will be in this part of the curve, and then in the middle you have this your optimal hyperplane. And this is how actually the radial basis function or the Gaussian hyperplane looks like. But there are multiple other kernel tricks. There are several, actually many different types. So here are some examples, and this is how you change your trick. So you have in linear trick, it's somehow looks like the y is equal to the slope function, y is equal to mx plus b. So this is just how that works, because it's a linear, so it uses a linear function. And you have a polynomial kernel. If you apply polynomial kernel, then this is how it goes. You have the p at the end, so that means you have the polynomial term, and then the radial basis function is like this one, the Gaussian equation. And there are multiple other kernel types that you can apply. The problem with support vector machines is you don't know which kernel trick very well fits with your data, so you have to try multiple different. There is no free lunch, so you have to try as many kernels as you can until you find the right kernel choice for which fits your data very well. This makes support vector machines to be computationally expensive. So depending on your number of observations and number of features you have, then you have to also add additional parameters like gamma, cost parameter. It's like penalization parameters to optimize your algorithm. So you have to fine-tune your algorithm, and then on top of that you add the kernel choice, and the kernel calculations is something which really makes it support vector machines very slow. So we will see some support vector. We will train support vector machines for our text data. So we'll first use quantitatext quantitatext models package, and then we will train like a very quick model, which may take super fast. Quantitatext model is very fast, but later we will also see the E1071 package for training support vector machines, which is more flexible, but of course more slower, and we have to tune it ourselves. Yeah, so that's how support vector machines theoretically look like. There is a lot of multiple other resources that you can look at. I think there are many videos which can explain support vector machines better than I did here, and there are many other resources. I invite you to have a look. Having said this, thank you very much. Thank you for watching, and thank you for being continuing to be as family for our channel. Thank you.